This set of notes is about collision theory and activation energy. As usual, there is a set of notes in Schoology that you can work with, or you're always welcome to take your own. All right, way back at the beginning of this unit, we talked about general things that can affect the rate of a reaction. And now that we've started to talk about rate laws, we can kind of talk about how those factors incorporate themselves into the rate law itself. All right, so rate laws themselves focus on the effect of concentration of chemicals on rate, right? If you think about it, we have that rate equals K times the concentration of X to some power N, right? So again, this here is focusing on how does concentration roll in there. But we know that there are other factors that influence how fast a reaction happens. So where do we see those in a rate law? Well, they're all wrapped into our K. All right, so things like temperature. Okay, so K changes based on different temperatures. Homogeneity of the mixture, okay, which is going to be a factor of what state of matter the substance is in. Surface area, presence of a catalyst, all of those things get wrapped into the rate constant as well as into the order of the reaction. Okay, so that's where those things get accounted for. So we do need to then spend a little bit more time talking about what are the factors that get wrapped into K and get wrapped into that reaction order. All right. So those factors can be explained by the collision model. Okay, the collision model basically says that in any reaction, okay, in order for a reaction to happen, you have to have bonds getting broken, okay, and you have to get new bonds getting formed. Okay, in order for bonds to break and bonds to form, you have to have atoms colliding with one another. Okay, collisions are required to break a molecule or break atoms apart, and they're also required to get atoms close enough together that they might attract, right? That they might attract and create some new bonds. So you need a collision for both breaking and making bonds. Okay, so if we're talking about rate, then what is it about collisions that are going to make a reaction go faster or slower? Well, one thing that affects the rate of a reaction, or how fast a reaction is going to happen, is going to be that collision frequency. Okay, and the reason for that is when you have more frequent collisions, that means that there's more chances that a collision is going to result in a reaction, and as a result of that, you end up with a higher rate. Okay, so there are some sub-factors then that will impact frequent collisions. How do you make atoms collide more often? Well, one way is through higher concentration or more pressure. Okay, this would be the concentration factor in our rate laws. All right, this one is pretty self-evident, right? If I've got more concentration, that means it's more crowded, okay? And if it's more crowded, that means I'm going to have more collisions. And if I have more collisions, there's a higher chance that one of them is going to be able to react, and so you end up increasing the rate. Okay. Another way to get more frequent collisions is to have higher temperature. Okay. If you have higher temperature, the particles are moving faster. If they're moving faster, that means that they're approaching one another more often, more frequently, and so as a result of that, you're going to end up with more frequent collisions. More frequent collisions means more chances to react, means a higher rate. Okay. Last thing that can affect the frequency of collisions is the surface area. Okay. So if I'm thinking about these magnesium particles down here, okay, they've got some surface area, right? And in order to make that reaction happen, you have to have collisions, okay? So right now, these particles that are around it, the acid particles and the water molecules, can collide, but they can only collide with these particles that are on the outside. None of the particles on the inside have a chance to collide. Well, if we increase the surface area and break those magnesium particles into smaller particles, they now suddenly have a lot more surface area. So the chances of having a successful collision is much more possible, or will be much more frequent, because the particles can get, all the particles can get smacked into. Whereas when they're stuck together and there's less surface area, then you don't have that same opportunity. Second factor that affects how frequently collisions can be successful or affects our rate is the orientation of molecules. Okay, so when the particles collide with one another, you have to have correct parts of the molecules colliding to make an effective collision. Over here, I have the reaction of nitrogen monoxide and ozone, hopefully trying to make nitrogen dioxide and oxygen molecules. Okay, well, in order for that to happen, as it shows down here, you have to have the nitrogen from the nitrogen monoxide hit one of the ends of the oxygen molecule. Okay, if it doesn't do that, you're not going to have enough energy. You can't certainly break the particle apart by smacking into the middle oxygen. You can't break the particle apart and make a new bond by having oxygen smack into oxygen. So both of those are going to result in ineffective collisions, collisions that do not create a new bond. But if you have this nitrogen hit one of the oxygens on the end, it can knock that oxygen off the molecule, and you get an effective collision that ends up pulling that oxygen on and attaching it onto the nitrogen, and you get nitrogen dioxide, and then what's left over is the oxygen molecule. Okay, so you have to have correct parts of the molecule. In other words, specific atoms have to hit other specific atoms to make a collision effective, to make a bond break and a bond be made. Correct collision orientation, if it's more probable, you're going to have a faster reaction. Okay, so how do you make a more probable orientation? Well, that's affected by the shapes of the molecules. If you have simple molecules, like the ones depicted here, the chances of this nitrogen hitting an oxygen that's the end are fairly high, much higher than if we had a much more complex molecule where you had to get specific parts of it to run into other specific parts of it. Okay, so again, shapes and sizes of molecules are going to affect how often a collision will be in the correct orientation. Third thing that affects the rate is the energy of the collision. Okay, so reaction collisions need to be strong enough to bend, stretch, break, and remake bonds. Okay. That collision energy, that energy that's needed for those particles to be able to make and break in bonds, is called the activation energy. We abbreviate it EA. Okay, and it depends upon a couple different things. It depends upon the strengths of the bonds broken and the arrangement of the molecules in the process of breaking and making. Okay, the lower the activation energy, the more collisions are able to overcome that activation energy, so the faster the reaction you have. Okay, so I love this little graphic over here showing us our different frogs. All right, and you got some dry frogs over here, and you got wet frogs over there. Wet frogs are to symbolize your product. Dry frogs are to symbolize the reactant. And in order for the dry frogs to get wet, they've got to get over this barrier. Okay, well, these frogs are going to jump, and if they don't jump high enough, every time, they're going to smack into the wall, and they're going to get bounced back. Okay, the chances of them getting over the wall, though, are a lot higher if that activation energy barrier is shorter. Okay, so again, what affects the activation energy barrier? Well, how strong the bonds are that need to be broken, and the arrangement of the molecules in the process of breaking and making them. Okay, so that's one factor. Okay, so now you might also say, well, one other way to get me to take care of this activation energy barrier would be to have frogs that can jump higher. Okay, so how do we do that? Well, that's the other part of the energy of collision effects rate equation, right? Reaction collisions need to be strong enough to stretch, bend, break, or remake bonds. Okay, so how can you get those frogs stronger? You can put them at a higher temperature, right? Because if we take a molecule and we put it at a higher temperature, that means it's going to have a higher kinetic energy, means it's going to be moving faster, so that means more collisions can overcome the activation energy, and the reaction will get faster. Looking back at our good old friend, the Maxwell-Boltzmann equation, you can imagine that if this amount of kinetic energy on the bottom here represents the amount of energy that's needed to get the frogs over the wall, the activation energy, right? At a lower temperature, you're going to have your distribution, so this many particles have enough energy to get over that activation energy barrier. But as soon as we raise the temperature, we know that that takes our particle distribution and stretches out here to the right. And as soon as you do that, you end up with a much larger fraction that are going to be able to get you over that activation energy barrier. Okay, so two factors to the energy of collision effects rate equation. One, okay, how strong can we make the collisions themselves stronger by increasing their speed? And two, what is the barrier that the strength of the barrier we actually need to get over, the size of the activation energy. All right. So Svante Arrhenius, who was a Swedish chemist, took all of this information and through mathematical manipulation and different experimental data, he actually created an equation that fairly well approximates how these factors go into the rate constant K. Okay, so here's our rate constant K, and that rate constant is equal to A times E to the negative activation energy over the gas constant times the temperature. Okay, so what are those different things that are part of this equation? Well, obviously K is our rate constant. A is our frequency factor. Okay, so this is basically a factor that tells us how frequent is a reaction collision going to be. So it incorporates both orientation and collision frequency underneath specific conditions. So A will be different at different specific conditions. Okay, EA obviously is the activation energy itself. Okay, and then R is the gas constant and T is the temperature in the Kelvin. For the purposes of AP, we do not actually need to do calculations with the Arrhenius equation, but we do need to understand what the effect of manipulating different parts of this equation are on K. So for example, one effect, as temperature goes up, reaction rate goes up. Okay, so why does that happen? Well, again, mathematically, if I take this and make this T bigger, it's going to make this exponent have a less negative power, so that's going to make my rate equation go up. Okay, so one effect of this is that as temperature goes up, rate goes up. So the rate constant is temperature dependent. One application of the Arrhenius equation is that you can actually use it to determine what the activation energy is for a particular reaction under certain conditions, as well as what the frequency factor are. Okay, so manipulating this very quickly, if I take the natural log of both sides of the Arrhenius equation, I get an equation that looks like this. The natural log of K, the natural log of K equals negative activation energy over RT plus the natural log of the frequency factor. Okay, we've been doing a lot this unit so far, but you'll recognize that that is actually a linear equation. Okay, y equals mx plus b. So if you find what K is at a few different temperatures, you can actually go ahead and graph that out. Okay, so if we ran our crystal, for example, if we ran our crystal violet lab at different temperatures, okay, and what you tried to do in each of those things is you plotted what your K was. You figured out what your K was at each of those different temperatures using the graphs that we developed in the lab. Okay, so once we have that, if we go ahead and we take the natural log of those different Ks and graph it versus 1 over the temperature, then the slope of this thing is the activation energy divided by the gas constant. The other thing that works out with this is the natural log of the frequency factor becomes our y-intercept. So occasionally in test questions and other places, you will see a graph come up with this. And so it's, once again, super important to go ahead and know that when you see a graph of the natural log of K versus 1 over T, that what they're trying to get you to do in this particular information is be able to figure out the activation energy as well as A. That's it for collision model stuff. Have a good day.